So now let's look at some common shapes of data distributions and how they're related to the mean, median, and mode. We're going to first start with a skewed right distribution. So this first graph here, a histogram, is what's called skewed right. Sometimes it's also called positively skewed because right, we associate positive with going to the right on the number line. Now, with this shape, the tail on the right side of the graph is longer. So if you imagine that you draw a smooth curve along the tops of the bars, we have a right tail that stretches out. Now, this means that most of the data is clustered in this mound area, but you have a few data values over here that are unusually big compared to the rest of the data set, and that is what is causing the tail to go to the right. So, for example, something that might have a skewed right distribution, if you have like a neighborhood where most people have moderate incomes, but we have a few very high earners that pull the mean to the right. So when we look at this distribution, the majority of the data falls in this area. This is going to be where the median falls, somewhere in this area. And then because there are a few extreme large values, the mean is going to get pulled to the right. So the mean is going to be bigger than the median. And that is because there are a few larger values that pull the mean to the right. So to understand what I mean by pulling to the right, let's relate it to something that we're really familiar with. Let's think about test scores. If you were in a statistics class and the majority of people had a test score that was in the 70s, so your average might be, say, 75. But then maybe you have a couple of people in the class that really did well and got near perfect scores. And so they have a couple of grades that are in the high 90s or even 100. So when you have those higher values, a few higher values, it's going to make your average come up a little bit. So instead of your average now being around 75, your average might be in the 80s. So those few values that are extreme are going to pull your average up. And that's why when we have a skewed right distribution, the mean is going to be a little bit bigger than the median. Whoops, I just noticed I spelled that wrong. All right, let's look at the next graph. The next graph is what's called mound-shaped and symmetric. It could also be called one peaked and symmetric, or it could be called bell shape. There's all kinds of ways to describe this data set, but the basic idea is that you have one peak in the middle and it trails off evenly on both ends. So when you picture the shape of a mound shape and symmetric, if you imagine that you're drawing a smooth curve over the tops of the bars, you get that normal curve or that bell curve shape. Now, this shape is centered and balanced. So the majority of the values are going to fall near the middle of the graph, and you have just a few extreme values on each side that are about even on each side. So you're not getting it pulled out in any direction more extreme than the other. When you have this kind of distribution, the mean, median, and mode are going to be the same or very close. So they're all going to lie in this area here. The mean, median, and mode will all be close together. If it's perfectly symmetric, then they'll be exactly the same. But in real life, most data isn't perfectly symmetric. An example of a data set that might be this bell-shaped curve is when you have maybe the heights of a group of people, because you're always going to have, most people are going to fall within a certain range for the height, and you're going to have a few people on either end that are short or that are tall, so that it's going to be pretty evenly distributed. So typically, any kind of body characteristics like height, weight, and those kinds of things are usually mound-shaped and symmetric. Now let's look at the next graph. This is called a left skewed distribution, which is very similar to what we had up here, the right skewed. It's just pointing in the other direction. So when I draw a smooth curve across the tops of these bars, you're going to get a tail going to the left instead of to the right. Now, because you have a left tail, that means you're going to have a few extreme values on the left, which means they're going to be lower or less than the majority of the values. The majority of the values are going to fall in that mound area. And then you have a few extreme values over to the left, which is what's causing the tail. So let's write down, you're going to have a few extreme lower values causing, or I should say creating, a left tail. And because you have a few extreme values going to the left, that means your median is going to fall in somewhere here in where the mound is. But those few extreme lower values are going to make your mean come down. Your average is going to come down. So in this case, your mean is going to be to the left of the median in the direction of the tail. And so your mean is going to be less than your median in this case. Now, an example that you might see for a left skewed distribution might be age at retirement. Most people might retire between 60 and 70 years old, but you may have a few people that retire early and it pulls the mean down. So you have some extreme values of people that might be retiring in their 50s, but most everybody is retiring in their 60s and 70s. All right, let's look at the next graph. This is called uniform. And this is where outcomes are equally likely. So it creates like a flat, even shape across the entire range of values. So they're all similar frequencies. Now, in real life, of course, you're not going to get the exact same frequency right across the top. That's going to be rare. But as long as it's close to being flat, that's going to be called uniform. Now, an example of when you might have a uniform distribution, if every locker at a school was assigned randomly and each number was used an equal number of times, the distribution of locker numbers would be uniform because you have a random chance of getting these numbers. So each one is going to occur about the same number of times. Now, in this case, when you have a uniform distribution, in this case, your mean and median would be the same or close together. And then your mode would most likely, for the mode, you would most likely have none. because if you all have a frequency that is about the same, then you're not going to have one value that occurs more than the other. So if it's exactly symmetric, you're not going to have any mode. Now, the last graph, this is what we call bimodal, or you could have more than two modes, which is called multimodal. But in this case, we have two modes, so we'll call it bimodal. And this is when you have two peaks or two high points. So when I draw a smooth curve to go over the bars, we have two peaks. So this occurs when we have data that comes from two different groups that are mixed into one set. So a good example might be a distribution of test scores in a class where some students studied really hard and some didn't prepare at all. So you have a bunch of really high grades. So that would fall in this area. And then you have a bunch of really low grades, which would be in the peak that's in the lower end of the number line. So you have a result of two clusters of scores. So this is a case where you would have two modes. The mode would fall in here. That would be the first mode, and then here would be the second mode. Now, for the median and the mean, it would fall somewhere in between. That's hard to say where the mean and the median would be. That would just be up to each data set, what happens in between those two peaks. But the mean and the median would definitely fall between those two peaks.